A spacecraft passing through the asteroid belt at 16,000 miles an hour was never supposed to find water there. Not on that rock, not in that part of the solar system. Not according to any model scientists had built over the last several decades of studying how our solar system came together. And yet, in April of 2025, NASA's Lucy spacecraft flew within 430 miles of a small, tumbling, peanut-shaped asteroid called Donald Johanson, and recorded something in its surface chemistry that should not have been there at all. It took the science team more than a year to confirm it, cross-check it, and publish it, because what they were looking at rewrites part of the story of where Earth's water actually came from. On June 18, 2026, that confirmation became official. And it is the kind of discovery that does not make noise the way an explosion does. It makes noise the way a quiet, undeniable piece of evidence does. The kind that sits in a peer-reviewed journal and slowly, irreversibly, changes what an entire field of science believed to be true. This is the story of Lucy, not the fossil, the spacecraft. A 12-year, billion-mile mission built to answer one of the oldest questions in planetary science. Where did we actually come from? And on its way to answer that question, it just found something nobody expected to find, on a rock nobody thought could be hiding it. NASA's Lucy spacecraft launched on October 16, 2021, from Cape Canaveral, on a 12-year journey unlike anything flown before it. Its destination is not a planet, not a moon, not a single target, the way most missions are designed. Its destination is a swarm. 2 enormous clusters of ancient asteroids called the Jupiter Trojans, trapped in a gravitational tug-of-war 60 degrees ahead of and 60 degrees behind Jupiter itself as it orbits the Sun. There are more than 15,000 known Trojan asteroids out there, locked in place for billions of years by the combined gravity of the Sun and the largest planet in our solar system. And scientists believe they are some of the most primitive, least altered material left over from the earliest days of planetary formation. Not fragments that were cooked, melted, and reshaped by billions of years of collisions and heat, the way most rocky material in the inner solar system has been. Frozen relics. Time capsules. Pieces of the raw material that built everything, including us, before that material ever had the chance to become a planet. To reach them, Lucy has to fly a trajectory so long and so complex that its first actual encounter with a Trojan asteroid will not happen until August of 2027, nearly 6 years after launch. But NASA did not design this mission to sit idle for 6 years while cruising through empty space. On its long path outward, Lucy was deliberately routed through the main asteroid belt, the vast ring of rocky debris between Mars and Jupiter, so that its instruments could be tested, calibrated, and put to real scientific use on ordinary main belt asteroids before the primary mission ever began. In November of 2023, that testing produced its first surprise, a flyby of a small asteroid called Dinkinesh that revealed, completely unexpectedly, that the asteroid had its own tiny moon, a satellite now named Selam, itself shaped like 2 lobes fused together, a structure scientists call a contact binary. Nobody had predicted that shape on an object that small. It was the first hint that Lucy's supposedly minor pit stops were going to matter far more than anyone had planned for. And then, on April 20th, 2025, Lucy reached its second target, an asteroid called Donald Johanson, officially designated 52246, named after the paleoanthropologist Donald Johanson, the scientist who discovered the original Lucy hominin fossil in Ethiopia back in 1974, the very fossil this entire spacecraft mission was named after. The symbolism was not an accident, just as that 2-million-year-old skeleton became a critical link in understanding the evolutionary chain that led to modern humans. The asteroid, Donald Johanson, was chosen as a rehearsal target, specifically because scientists believed it could serve as a link in understanding the evolutionary chain of the solar system itself. A fossil of the raw material that eventually became planets, moons, and eventually Earth. Lucy's cameras captured the asteroid in stunning detail as it swept past. What they revealed was a bilobed shape, 2 distinct rocky masses joined by a narrower, smoother neck, roughly twice the length of New York City's Central Park, end to end. Slowly tumbling, clearly ancient. And, as the mission team would spend the next year confirming, clearly the surviving fragment of something much larger that had been violently destroyed a very long time ago. Donald Johanson orbits the Sun in the inner portion of the main asteroid belt, a region of the solar system that, according to the standard models of planetary formation, has always been too close to the Sun, too warm, for large amounts of water ice to have survived there for long. Objects that formed with substantial water content are generally expected to have formed much farther out, in the cold outer reaches of the early solar system, where ice does not sublimate away under the Sun's heat. For an object sitting in the inner asteroid belt to carry a clear chemical record of liquid water interacting with its rock is, in the words of Simone Marchi, the planetary scientist at the Southwest Research Institute who led the study, genuinely intriguing, because it strongly suggests Donald Johanson did not form where it currently orbits. it likely formed much farther from the Sun, in a colder region of the early solar system where ice was abundant, and was later transported, relocated, flung inward by the same violent gravitational reshuffling that shaped the entire architecture of our solar system in its first few 100 million years of existence. Think about what that actually means. This is not simply a rock with an interesting mineral signature. This is a physical, chemical record proving that material carrying water was being moved around the early solar system, shuffled inward from the cold outer regions toward the warmer inner regions where rocky planets like Earth were forming. And that detail sits at the center of one of the biggest unresolved questions in all of planetary science. Where did Earth's water actually come from? Earth, as it originally formed, should have been dry. The region of the early solar system close enough to the Sun to form a rocky planet like ours was too hot for significant amounts of water ice to survive the process, which means every ocean, every river, every drop of water that eventually made life on this planet possible had to arrive from somewhere else, delivered later, likely by a bombardment of water-rich material migrating in from farther out in the solar system, colliding with the young Earth over millions of years. Scientists have debated for decades exactly what kind of objects did that delivering. Comets, certain types of asteroids, some specific combination of both. Donald Johanson, sitting exactly where it should not be, carrying exactly the chemical signature it should not have, is direct physical evidence supporting one very specific version of that story. That water-bearing material, formed far from the Sun, really was being redistributed into the inner solar system during its earliest, most chaotic period, potentially riding along on objects just like this one, objects that may have delivered exactly this kind of material to the young Earth itself. The data revealed something else, something almost as significant as the water signature itself. The aqueous alteration inside Donald Johanson, the actual chemical process of water interacting with and transforming its internal rock, appears to have stopped early, not continued for the full duration the asteroid existed, but cut short relatively soon after it began. According to Marchi, that detail is itself a clue. Aqueous alteration requires internal heat, typically generated by the decay of radioactive elements inside the object. And if an asteroid formed later than the majority of surrounding material in the early solar system, it would have had access to less of that radioactive heat, because much of it would have already decayed away by the time the object came together. In other words, the fact that the water process shut off early may be telling scientists something specific about exactly when, in the solar system's earliest and most violent stretch of history, this particular fragment of rock actually formed. Every one of these details, stacked together, functions like a forensic timeline, reconstructed from a spacecraft flyby lasting only a matter of minutes of an object that formed over 4.5 billion years ago. And there is one more layer to this discovery, one that connects it directly back to Lucy's true primary mission. Donald Johanson's violent, fractured history did not happen in isolation. Researchers determined that it is a surviving fragment of a much larger parent asteroid, one that was struck and shattered in a massive collision approximately 155 million years ago. The largest surviving chunk of that original parent body still exists today, a 45-mile-wide asteroid called 163 Aragon, and the entire scattered family of debris from that ancient impact, including Donald Johanson itself, is now formally known as the Aragoni family. That single act of cosmic violence, a collision that occurred while dinosaurs were still walking around on Earth, is directly responsible for the small, strange, water-bearing fragment that Lucy happened to fly past nearly 155 million years later. The bilobed, two-lobed shape connected by a narrow neck, the same basic structure, spotted on Donald Johanson, on the tiny moon Selim orbiting Dinkinesh, and on several other small bodies studied by other spacecraft across the solar system, appears to be an extremely common outcome of exactly this kind of violent collisional history, fragments coming back together under weak gravity to form what scientists call a contact binary. Different objects, different sizes, different regions of the solar system, all converging on the same basic architecture, shaped by the same basic physics of things breaking apart and slowly, gently reassembling themselves in the vacuum of space. Here is why all of this matters, for where Lucy is actually headed next. Among the Trojan asteroids waiting for Lucy at Jupiter, one target in particular, an asteroid called Euripides has already shown a spectral composition strikingly similar to Donald Johanson's, more similar to it than to any of the other Trojans on Lucy's itinerary. That similarity is not a coincidence scientists are willing to ignore. It raises the possibility of a genuine connection between Donald Johanson and the Trojan population Lucy is traveling more than 6 years and hundreds of millions of miles to study. If that connection holds up under closer examination, it would mean the violent, early shuffling of material that scattered Donald Johanson into the inner asteroid belt may be linked to the exact same process that captured the Trojan asteroids into their strange, locked orbits around Jupiter's path. One dramatic, chaotic period in the solar system's youngest years, visible in the chemistry of two completely different populations of ancient rock, separated today by hundreds of millions of miles, but connected by a shared origin billions of years in the past. Marchi and her team are already framing the next phase of the investigation around a much bigger question. If Donald Johanson was relocated from the outer solar system into the inner asteroid belt, carrying water and organic material along with it, how many other objects made that same journey? How many other water-bearing fragments were scattered inward during that same chaotic period, some of which may have eventually collided with the young Earth, delivering exactly the raw ingredients life would eventually need? Every one of those objects would represent a piece of the answer to one of the single biggest unresolved mysteries in planetary science: how a hot, dry, rocky planet formed close to the sun ended up covered in oceans. None of this required a dramatic close encounter with danger. Lucy did not almost fail. It did not send back a garbled signal that frightened engineers at mission control. This is a different kind of space story, quieter, slower, built entirely on patient analysis rather than crisis, and in some ways that makes it more remarkable, not less. A spacecraft flew past a small, tumbling rock for a matter of minutes, on its way to somewhere else entirely, and in that brief window of data, it captured evidence bearing directly on the origin of water, the origin of the ingredients for life, and the violent, chaotic reshuffling that built the solar system we live in today. It took scientists over a year of careful spectral analysis, cross-referencing, and peer review to confirm what they were actually looking at, and only in June of 2026 did the full picture become public, published in the journal Science, standing now as one of the most significant findings of Lucy's entire mission so far. And Lucy has not even reached its primary targets yet. That is the part worth sitting with. Everything described here, the phyllosilicates, the ancient collision, the possible link to Earth's oceans, the connection to the Trojan asteroids waiting at Jupiter, all of it came from a single brief flyby of a secondary target, a rehearsal, a test run before the real mission even begins. Lucy's first true encounter with a Jupiter Trojan asteroid, Euripides, is scheduled for August of 2027. 5 more flybys follow after that, stretching all the way out to March of 2033, when Lucy is scheduled to reach its final target, a remarkable, near-twin binary pair of asteroids called Patroclus and Menoetius. If a quick pass by a minor asteroid on the way there produced a discovery this significant, one capable of reshaping how scientists understand the delivery of water across the early solar system, it raises an obvious, almost unavoidable question. What is waiting for Lucy when it finally reaches the objects? This entire 12-year mission was actually built to study. Consider for a moment just how easily this entire discovery could have been missed. Donald Johanson was never the point of the mission. It is not one of the 8 primary targets Lucy was built and funded to study. It was, in the plainest engineering terms, a convenient waypoint, an object that happened to sit close enough to Lucy's planned trajectory that mission planners could justify a flyby purely as a technical rehearsal, a chance to test cameras, calibrate instruments, and practice the delicate choreography of a high-speed close encounter before the stakes became permanent. Lucy does not get a second attempt at any of its targets. Every flyby happens once, at speeds up to 16,000 miles an hour, with a spacecraft that cannot slow down, turn around, or come back for another look. The Donald Johanson encounter existed specifically so that if something went wrong with the cameras, the targeting, or the timing, the mistake would happen on a rock nobody was counting on, rather than on one of the ancient Trojans the entire 12-year mission was actually designed around. And instead, the rehearsal became one of the most scientifically important encounters of the mission so far. That is not a small irony. It is a reminder of something that keeps happening across the history of planetary exploration, that some of the most consequential discoveries arrive not from the objects scientists expected to be significant, but from the ones treated as afterthoughts, squeezed into the itinerary because the trajectory happened to allow it. New Horizons found an unexpectedly complex geologically active Pluto after being built to fly past what many assumed would be a simple, frozen, unremarkable ball of ice. And now Lucy, on a routine calibration flyby of a minor rock in the inner asteroid belt, found direct physical evidence bearing on one of the biggest open questions about the origin of life on Earth. There's also a deeper, quieter significance to the timing of what Lucy found, one that connects directly back to the reason the mission carries the name it does. The original Lucy fossil, discovered by Donald Johanson in 1974 in the Afar region of Ethiopia, mattered so profoundly to the study of human evolution, not because it was flashy or dramatic, but because it filled in a gap, a missing link connecting earlier and later stages of the evolutionary record. The asteroid named after him has now done something structurally similar, for an entirely different kind of evolution. It has filled in part of the missing link in the story of how the solar system's raw material was redistributed, how water first found its way from the frozen outer solar system into the warm inner region where Earth eventually formed. That patience, the year-long gap between the actual flyby in April of 2025 and the published confirmation in June of 2026, says something important about how real scientific discovery actually works, especially compared to how it often gets described online. There was no single dramatic moment where an alarm went off in a NASA control room. There was a long, careful process of downlinking data across millions of miles of space, cross-referencing spectral readings against laboratory models of exactly how different minerals absorb and reflect sunlight, checking the phyllosilicate signature against every plausible alternative explanation, and only then submitting the findings for peer review in the journal Science. That is not a system built for speed. It is a system built for accuracy, one careful enough that when a claim like this finally does get published, other scientists across the field can trust it and build on it. And the next set of questions is already forming. If Donald Johanson really did migrate inward from the outer solar system, carrying water-altered minerals with it, then it was almost certainly not alone. The same violent, chaotic reshuffling of material that flung this one object into the inner asteroid belt would have redistributed countless other fragments at the same time, an entire population of water-bearing debris scattered across the young solar system during its most turbulent early history. Some of that debris may still be sitting quietly in the asteroid belt today, waiting for a future mission, or perhaps waiting for further analysis of data Lucy has already collected to be identified and studied. Some of it may have been swept up and incorporated directly into the forming Earth billions of years ago, its water becoming, quite literally, the water in the oceans, covering most of this planet right now. There is no way yet to know exactly how much of Earth's water arrived this way, versus through comets or other delivery mechanisms scientists have proposed over the decades. But there is now, for the first time, direct physical evidence sitting in a peer-reviewed journal that this specific pathway, inward migration of water-rich material from the outer solar system, genuinely happened, and genuinely left a traceable signature behind on at least one surviving fragment. Lucy, meanwhile, keeps moving. As of August 2026, the spacecraft has already begun turning its cameras toward its future Trojan targets, months ahead of the actual encounters, capturing early test images of asteroids named Euripides, Polymele, Lucas, and Orus from hundreds of millions of miles away, still nothing more than pinpricks of light against a field of background stars. Engineers are using those early images to fine-tune camera settings, exposure times, and targeting precision, preparing for a sequence of flybys that will begin in August of 2027 and continue through November of 2028, each one lasting only minutes, each one representing the only opportunity humanity will ever have to study that specific object up close. Given what the Donald Johanson rehearsal just revealed, the pressure on those upcoming encounters has quietly, significantly increased. If a minor waypoint asteroid could rewrite part of the story of Earth's oceans, the question now sitting with every scientist on the Lucy team is unavoidable. What is actually waiting inside the Trojan swarm? In objects believed to be even older, even more primitive, even less altered by billions of years of solar system history than the rock that just delivered this discovery, the rocks that built our solar system are still out there, tumbling silently through the dark, carrying chemical memories of collisions that happened before dinosaurs existed, of water that moved from the cold outer reaches of the solar system into the warm inner world where Earth eventually formed oceans and eventually us. Lucy is still flying toward them, and based on what it just found in a rock nobody expected to be interesting, the biggest discoveries of this mission have not happened yet. If stories like this fascinate you, the quiet discoveries that quietly rewrite everything, subscribe, because Lucy is still out there, still flying, and its first real encounter with the Trojans is only a little more than a year away.